Okay, in this video we're going to be talking about some of the concepts, applications, and limitations of IR and Raman instrumentation. It's important to remember that IR spectroscopy is an absorption technique. Raman is a fluorescence technique. In IR and in Raman spectroscopy, we still have to hold to the same basic block diagram. We have a source, we have a sample, and we have a detector. It's important to remember that detectors are wavelength specific still. We can both detect the number of photons and have some specificity about identifying the wavelength of the photon studied. We're really just going to be studying, in this case, what are the purposes of the source, what are the optics for the sample, and what are the applications and limitations of these techniques. In IR spectroscopy, we really just need a source that is going to produce wavelengths in the IR region, specifically heat. This is best done using what is referred to as a Nernst glower. Really, just about the same thing as a toaster filament. You run a bunch of current through a nichrome wire, it gets red hot and gives off heat. The optics is really what gives us a problem in IR. Remember, the optical material has to be transparent in the wavelength region of interest. And glass, plastic, quartz, all of those things have bonds that absorb heavily in the IR region. So, just like the car that gets too hot because all of the IR is absorbed by the glass, we can't use glass, plastic, quartz, any of our typical materials to create an optically transparent material. So you're really stuck in IR using crystalline structures that aren't similar to the organic molecules. Originally, they used things like sodium chloride and KBr pellets, which pretty much lets out the use of aqueous solutions because it would simply dissolve the optical material. And now we can use crystals like diamond anvils and things like that, but it's very expensive and very difficult to use. So solutions are difficult largely because of the optical materials that have to be used. The detector, we have to detect heat. So really, the detector is the equivalent of just a thermometer, a thermocouple, or some transducer that can convert heat into electrical current. This is not very sensitive, but since IR is an absorption event, you still have to have the detector directly in line with the source, and that means that we don't need high sensitivity detector, we need high dynamic range. IR works for most molecules. It is specificity in the bonds that it's analyzing, but it's still an absorption event, so it has high dynamic range and reasonably low sensitivity. The source, when we're talking about Raman, is different. We're talking about now a fluorescence event. And the purpose of the source in fluorescence is put it in an excited state. Nice thing about Raman is it doesn't have to be resonant with the transition. It can be any wavelength you choose. The downside is it can only be one wavelength. We want to know the exact energy of the wavelength being emitted that will promote it into the virtual state. And that means the best source for Raman is a laser. Lasers are unique because they do put out monochromatic light. One wavelength. If we know the energy of the input photon, then we can calculate the shift based on analyzing the Stokes and anti-Stokes emission that is released. As I said, the purpose of the excitation is simply to put the molecule up to some virtual state. It is then going to be scattering both the Rayleigh scattering, which will be at the exact same wavelength, and also some Stokes and anti-Stokes. But because it's a fluorescence, it can be going in any direction it wants. That means, just like in any other fluorescence experiment, we can put the detector at 90 degrees to the source. It means all that extra emission from the source will not be detected by the detector, and we don't have to differentiate it from the photons that are being released. Now we are talking about the emission of visible photons. In our previous example, if this is a carbonyl and we put in 632, the Stokes emission would be coming out still in the visible range as a red photon at 708. The type of detector we're detecting now is going to not detect IR, but it is going to detect the visible Stokes emission. That means that we can use a photomultiplier tube as our detector. This is incredibly sensitive. So if we look at the number or the emission of the Stokes, it is going to be directly proportional to the concentration of the sample. We can use Beer's law to quantify using the fact that the Stokes emission will be directly proportional to the concentration. This has the added advantage of a fluorescence technique which provides a geometry of the instrumentation that provides high sensitivity but also specificity due to the structural dependence of the Stokes emission. This 708 that is being emitted can only come about from a molecule which has the carbonyl, because it is shifted by the exact energy. So if you know the input energy and you observe a Stokes emission, that Stokes emission can be tracked back to the specific vibrational mode of a molecule. We can therefore do highly specific quantitative analysis at extreme sensitivity because of the geometry and the use of a highly sensitive detector.